We just now looked at a very surprising and interesting result, which says that on a graph, if we have n nodes, then one just needs n log n number of edges to make this graph connected. That is, if we take n nodes and we randomly put n log n edges in this graph, the graph becomes connected. So you can start at any node in this network, and from this node you can find a path to every other node in the network. Now we will be doing a screencast for it. We will be writing a piece of code in which we will take random graphs of different sizes, and then we will look at the number of edges required to make this graph connected. So we will do this, we will look at the plot. Let us get started. Let us start from very basic coding. So what we want to do is, we want to have some nodes in the graph, and then we add random edges in this network one at a time, and our aim is to see after addition of how many edges does this network becomes connected. So we first create a file for this. So let us open a new file in Notepad. Let us name it as connectivity.py. So here we have a file. So we first of all import our basic packages which we will need. Import network access nx, say I think it is sufficient for the time being. Okay. So what we do, we first define a function to add some specified number of nodes in the network. So the function already exists in network X, you all know, but just for the sake of simplicity and clarification, I will again make a function here, and let us name this function as add nodes, and you pass a number n as a parameter to this function. So what this function is going to do is, it will create a graph g equals to nx dot graph and add n number of nodes in this graph. So we can do g dot, I hope you remember the function add nodes from. So this function adds the nodes in the graph from a list, and the list we give here. So the list is from number 0 to number n minus 1. So n nodes get added to this graph, and we finally return the graph. A simple function. We will just keep commenting everything side by side. So we comment it, add n number of nodes in the graph and return it. Perfect. So let us save it and let us come back to our window. So what we need to do now is import this file. We import connectivity. So this gets imported. Let us call our function. So to call our function, we have the syntax connectivity dot function name. Our function name is add underscore nodes, and we had, let us say we want to add 10 nodes in the graph. We execute it. So we get a graph here. So our function returned a graph. So let us collect the output in a graph named g. So g equals to connectivity dot add underscore nodes 10. Now I want to see whether 10 nodes have been actually added in the graph or not. So we can see that using the function g dot number of nodes. You can see that there are 10 nodes in this graph. Next, we will write a function for adding one random edge to this network. So if you see currently in this network, there are just 10 nodes, there are no edges. So this network is disconnected, completely disconnected. So to check that, we have a command nx dot is connected. Let us say we want to see whether this graph is connected or not. Let us call, okay, so before using, nx dot is connected, pass the graph g here. So it shows us false, the graph is not connected. Okay. Now one by one we add edges to this network. So first we write a code for adding one random edge to this network. We go back to our file which was connectivity.py, and now we add a second function here, and the function is for add one random edge in this network, add one random edge. Let us name the function as add random edge, and it takes as input the graph G which has been already created with no edges. So, we pass that graph G. Actually, you can pass a graph G with edges also, that is up to us. So, the function takes as input one graph and adds one extra random edge to this graph. So, define add underscore random edge G. Now, we need two random vertices from the network. So, how do we pick a random vertex? So, to pick a random entry, we need one package named random. So, we have discussed about it before in the first week. What does it do? We are going to use the function random.choice. First vertex V1. So, this is the first random vertex which we want to pick. It is random.choice. Random.choice function takes as input one list and outputs us one random value from that list. So, the list which we are going to pass here is g.nodes, that is the list of nodes in the network. So, V1 gets first random node from this network. Let us choose another node V2. V2 equals to another random node random.choice, and again we have here g.nodes. We got two random vertices now and we want to create an edge between them. But there might be a case where V1 and V2 might be same nodes. So, we would have picked both the random nodes to be same, although that is a very rare case that might happen, but we do not want that to happen because we do not want any self loops in our graph. So, we just put a condition here, if V1 is not equals to V2, only then we add an edge, that is these two vertices should be separate. So, if V1 is not equals to V2, we go ahead and add an edge, g dot add edge from V1 to V2. After adding this edge, we return our graph G. Save it, we come back to our console. Now we need to reload our file. So, we reload connectivity since we have made changes to it. Reload connectivity, I hope the spelling is correct. Reload connectivity, okay. So, it is reloaded. We already have a graph here which has 10 nodes. So, what do we do now is G equals to connectivity dot, and we call our function add random edge on the graph G itself. Okay. Seems to be some problem. So, it is a name error which says that global name, okay, there is a spelling mistake. So, let us go back and correct it. So, if we see here, yeah, this small spelling error, we correct it, save it, come back, reload it and call the function again. So, it worked fine. So, we now one random edge should have been added in our graph. So, let us see it. Let us look at the list of edges in our graph. So, we do g dot edges and we can see here that a random edge, an edge has been added from two vertices 0 to 7. So, we have written the code till now for adding a specific number of vertices in the graph and adding one random edge. What is our aim? Our aim is to keep adding these random edges in the network till our network becomes connected, and then to look at how many edges were these which made this network connected. So, for doing that, we go back to our code and let us create another function here. What this function does is it add random edges. Let us rather say keeps adding random edges in G till it becomes connected, and let us name this function as add till connectivity. Add till connectivity, and it takes the graph G as input. So, what it is going to do till the graph becomes connected. So, while nx dot is connected G. So, this is a function in network X which returns true if the graph is connected, false if it is not connected. So, while nx dot is connected G is equals to false, it keeps running, and what does it do? It adds one random edge to the graph. So, our graph G becomes add random edge G. So, one random edge is added to this graph and it keeps adding more random edges till the graph becomes connected, and at the end let us return the graph. So, let us look at what this code is doing. Again we reload connectivity, and now what we are going to do is G equals to connectivity dot add till connectivity. So, let us see how many edges it adds. So, we already had one edge which we have added previously, and we pass the graph G here, and let us now look at G dot edges. So, we see that many edges have been added to this network. To be precise, the number of edges added is 16. So, it seems like in a graph having 10 nodes, just 16 edges are required to make this graph connected. Let us also quickly check whether it is connected or not. So, nx dot is connected G, we can say that it is, we can see that it is connected, it is true. Till now what we have done is we have written a small piece of code which takes a graph as input, keeps adding edges to this graph till the graph becomes connected. Next, what we want to do is to repeat this procedure for different number of nodes. So, here for example, in this we did it for 10 nodes and we looked at that the number of edges required was 16. Now, want to do it for 20, look at the number, want to do it for 30, look at the number, and so on. So, for doing that, first of all let us create a new function here. So, this function is going to simplify what all we have written here. Let us name the function creates an instance of the entire process. So, what do I mean here by instance of an entire process? It takes as input. So, this function will simply take as input number of nodes and returns the number of edges required for connectivity. So, it will make our task easier. So, we will just input a number n, a number of nodes, and it will output us, it will tell us how many edges are required to connect a graph having these many nodes. So, let us define this function, let us name it as create instance, and whatever is required inside the code for this function we have already done that. So, define create underscore instance and let us pass a number n here. What we do next is, first of all we have to add nodes. So, G equals to add underscore nodes and we add n nodes. So, we call the first function which we defined previously. So, whatever we have done till now in IPython, that only we are replicating here in the file. So, we first call this function add underscore nodes n which returns us the graph, and next we can simply call G equals to keep adding till the graph gets connected. So, add till connectivity and we again pass here G, and it will return us, what it will return us? The number of edges. So, return G dot number of edges. Okay. Let us see how is it working. We reload the file and let us call create underscore instance and let us pass the number 10 here. Okay. So, it is in our file connectivity.py. So, connectivity.create_instance 10. So, we see that if there are 10 nodes, we need 12 edges. Let us make it 20 nodes, we need 27 edges. If we have 30 nodes, it is 50 edges and so on. But what we are interested in, I want to plot this and visualize how does this plot looks like. So, we just need to plot what we have done. So, for plotting it, we go back to the file. We can define a function here. So, what this function do? Plot the desired, let us say we know what is desired. So, desired is the number of edges required for connectivity. Plot the desired for different number of edges. And let us define a function and let us call it plot plot connectivity. Okay. Let us define this function plot connectivity, and it does not require as input anything. We are not taking any input, for simply for different number of nodes we will plot it. So, for plotting always we need the arrays corresponding to our two axes, x axis and y axis. So, let the array associated with x axis be x and the array associated with y axis be y. So, we have here x and y. Then we take a number I equals to 10. So, I, what does I tells us? I is the number of nodes for which we are experimenting. So, I is the number of nodes while, and let us take the number of nodes till 100, or let us rather make it 400. So, while I is less than or equals to 400, what this loop will do? In x axis we append the number of nodes, which is nothing but I, and in y axis we can append, what do we append? The number of edges required to connect these many nodes, which we can get from our function create instance. So, y dot append create instance, and we pass I here, and we need, let us increment I with 10 every time, I equals to I plus 10. Now, we need to plot this. So, for plotting this we need the package matplotlib. We import matplotlib dot pyplot as plt. Come back. Okay. So, what do we do? Plt dot plot. What we want to plot is x against y, and plt dot show. So, let us just do a little bit of decoration here. Before plotting it, let us add some labels and the title for the curve. So, let us say plt dot x label, which is the label for the x axis, is nothing but the number of nodes. Plt dot y label, label for the y axis, is the number of edges required to connect the graph, and plt dot title. Let's give a title to this curve and let us title it as emergence of connectivity. So, it is done. Let us look at how does this plot look like. Save the file. We will reload it, and then we call connectivity dot plot connectivity. I will take some time to execute. Yes. So, here we can see the curve. Here we have the number of nodes, here we have the number of edges, and we can see that as the number of nodes increases, the number of edges required to connect it also increases. Although we see this plot where number of nodes with number of edges, we see a lot of spikes in this curve. So, why are these spikes occurring? It is because our experiment is a random experiment which gives a different output every time you execute it. So, whenever you execute a random experiment, it will give you a slightly different output. So, one time it can throw a value 3, other time 5, other time 4, but if you take the expected value, it gives you a better estimate. So, to remove the spikes in the plot, instead of taking one value corresponding to one instance, we might want to average it out. So, let us look at how can we do that. We go back. So, what are we doing here is corresponding to one value of I, that is corresponding to one particular instance, given a particular number of nodes 10 here, we execute this code only one time. So, we take a graph having 10 nodes, we look at how many edges are required to connect it, and then we return the number of edges. What will give us a better result is if we do it multiple times. So, we take a graph having 10 nodes, then look at the number of edges, we again do this, do it 10 times and take an average over all those experiments. That will give us a better estimate. So, let us try doing that. So, doing that is very easy. So, in this create instance, so create underscore instance is for one instance. You give it one number of nodes and it gives you number of edges. Let us average it over some particular number of instances. Let us average it over 4 instances. So, see what I am going to do here is we define a new function and let us name it create average instance n, and what it does is it calls the function create underscore instance 4 times and takes an average over them. So, we create a list here, list 1, and for I in range 0 to 4. So, it is repeated 4 times. What does it do is list 1 dot append. What does it append to list 1 is create underscore instance n. So, it appends it to list and what it returns is the average. So, it returns numpy dot average of list 1. So, we have yet not imported numpy. So, let us import numpy here, import numpy. So, it returns numpy dot average list 1. So, what we are going to do is while plotting in plotting connectivity, instead of using create underscore instance, now we use create underscore average underscore instance. So, the value is averaged over 4 particular instances. Now, let us look at the change in the curve it creates. We reload connectivity and we again call this function. So, since it is doing it 4 times, it takes some time, and you can see that the difference in two curves is visible. This curve is more smoother because we have averaged out the values over 4 instances where it was only one instance in this case. Let us play around with it a little bit further and let us change this 4 to let us say 10. So, we do an average over 10 instances, we make this 4 as 10, we reload it and we call the function again. Let us wait for the output. So, again you can see a visible change in the curve, it gets all the more smooth. So, you can change this value from 10 to 20 to 30 to 100 and the curve will become more and more smooth. So, you can try it for higher values. Now, the final and the biggest question, what was our claim was that if there are n nodes in the network, it takes just n log n number of edges to connect this network. The question is, are these number of edges n log n? So, if I look at this curve, is it the curve of n log n? So, let us write a piece of code and check that as well. So, what I am going to do is I am going to draw this plot. So, I am going to have 2 plots in the same figure. One plot is the plot which we have achieved from our code, which is the actual data, and let us plot it against n log n, and look at what is the result. So, I want a very smooth curve. So, for a very smooth curve, what I do is I average it to 100 instances. So, I average it for 100 instances, and now I want to plot it against the n log n curve. So, what I do is after doing this, before plotting, I do exactly the same procedure which is written above, but here I am going to plot n log n. So, whatever I am going to do here is simply a replication of the above code with a little bit of change, and you can write it as a separate function as well, but I am writing it here. So, I take a new array x1 and a new array y1, and then again I set I equals to 10, which is the number of nodes, and while I is less than or equals to 400, what I do is x dot append, x में simply I append I, y dot append is the curve I want, and the curve which I want is I multiplied by log I. Okay, sorry, it's x1 dot append and it's y1 dot append I into numpy dot log I, and then I increment I with 10 and I do plt dot plot x1 y1. So, it is going to show me two plots in the same figure, one is for xy, which is the actual data, number of nodes and the number of edges required to connect them, and second is the x1 y1, which tells me a number on the x axis, and if the number is I, it tells me I log I on the y axis. Again reload the file and let us run it, and let us give it some time to execute. Since it is averaging over 100 instances, it will take some decent amount of time. Okay, the code here ends with an error and it is again a spelling mistake. Let us go back and correct it. So, just correct it here, and what we do here is I have added an extra statement here, print I, which keeps showing us how many iterations has the code completed. So, for the time being, let us make this I 200, since for 400 it takes a lot of time. So, let us see how does it work for 200. But if we see our code below, so for the second plot, it is still plotting till 400 nodes. So, we also change this and make it here 200, and now we just save this code and let us run it. So, let us reload our file and we call our function connectivity.plot connectivity. So, here you can see two lines in this plot. One is the blue line, which corresponds to our data, where we took different number of nodes and looked at the number of edges required to connect the corresponding network, and the red line, it corresponds to the n log n plot. So, the lines are not totally overlapping in this case. So, here I would like to remind you that according to the analysis that we have done, the number of edges required to connect the graph was not exactly n log n, it is of the order of n log n. So, let us do a little bit of tweak in our code. Let us go back to our notepad file, and what I am going to do here is, instead of plotting n log n, what I plot here is n log n divided by 2. So, please note that even if I divide this term n log n by 2, in the final analysis the number of edges required to connect the network still remains of the order of n log n. So, let us try doing that. So, what I do here is I divide the term log n by 2, and let us see how our plot changes. Let us plot it. So, here you can see that both the curves, they come very close to each other, establishing the fact that it is essentially n log n by 2 number of edges, almost of the order of n log n, which are required to make our graph connected, hence satisfying our previous claim.